In this two-part series, we will create a neural network and backpropagation from scratch. The implementation will be GPU enabled with amazing performance. Against the standard neural network implementation from PyTorch, our implementation from scratch trains much faster. The task our neural network will perform is handwritten digit classification using the MNIST database. So, without further ado, let's begin. Alright, so to create a neural network, we first need a class called neural network. So we'll start by defining that class. And we have to first define the constructor. And the constructor will take in self, and we will create a variable called layers, because this is what will hold the neural network's layers. Another variable is the loss, because that's what we have to save once we evaluate the model. Next, we can define the forward method. And the forward method is what will take an input and actually create an output. So first, X is the initial input layer. And we'll create a for loop that goes through each of the layers in our layers list. The first thing we do is that we'll calculate the set value, which is before we use the activation function. And that is just by calling layer.forward on the current input to the layer. And then using the set value, we can actually calculate the activation value for each of these neurons. And we'll use the ReLU because it's been proven to work very well. Now, to define the ReLU, we need to import torch. And because that allows us to use torch.maximum that takes either the value or 0, because in ReLU, all activation values that are below 0 just returns 0. Otherwise, it's just a linear function. Then we set the current layer equal to the output of the current layer that we're working with, because that allows us to use that as input to the next layer. Finally, the output is calculated using forward on the last layer. Alright, but what is a layer? We haven't defined that yet. So we need to create a class that is called layer. We have to have a layer class. So let's define the layer class, and we'll create the constructor for the layer. And the layer will take an input dimension and an output dimension. Then we also need the weights for each of these neurons in the current layer. And we'll initialize them with torch.random, and we'll do very low weight values by just multiplying by 0.01. Next, we also have to initialize the bias, which is just a normal array. And we'll just initialize them to 0. Finally, the inputs to the layer is none. So the inputs variable has a shape of batch size and input dimension. And this is because we want to be able to calculate multiple inputs at once using the GPU. So it's a matrix where each row is an input. And the layer also needs a forward method, and it takes the input batch, so a list of inputs. Then we'll calculate the set values by taking the input batch and multiplying it with the weights. This is a matrix multiplier. And then we'll return the set values. And this is what the forward method in the neural network class uses when it then calculates the ReLU values. Next, we actually have to be able to add a layer to our neural network. So we'll create a method called addLayer, and it takes in a layer. And then we add it to the layers list. And we'll do a little trick and we'll return self, because this allows us to initialize a neural network like this. Then we can just do add layer and it will return self. First we'll initialize the layer with 784 inputs. Then we'll just add another hidden layer, and finally the output layer that contains 10 output neurons . Alright, now we're ready to actually accomplish the task. We've created a standard neural network that can be used to solve many tasks, but we have to be able to classify handwritten digits. We'll start by importing pandas and creating the data frame containing the training data. And we'll do that using pandas read CSV. And I have my training data at this path. And now let's take a look at what is inside this data frame. And as we can see, we have a matrix containing in the first column the labels the image represents, and then the rest of the columns in the row are all the pixel values, and there are 784 pixel values. Alright. Then we have to define the training set and the test set. And we'll do that using the train test split, and we'll have to import the sklearn to get access to this method. And we'll also import the data loader and the dataset from the Torch library, because we'll need that in a moment. The train test split takes as input the data frame, the test size, which we'll set to 20% of the data set. We'll set a random state of 42, and we'll do stratify. And stratify just makes sure that the distribution of different digits stays the same between the test and the training set. Alright, and now we need a class that can pull out a single sample from the training set. And the class takes a variable called labels. That is just the first column of the data frame, and the rest are the pixels. We'll also have to define the length method, and that just returns the length of the labels. And now we'll define the getItem method, which just takes a single sample. And that's it. Now we can create the training dataset and the test dataset by using this class. And we'll make sure to just reset the indexes just so that both the training dataset and the test dataset starts with index 0. Alright, now we create the train loader with the use of the data loader. And that takes the dataset and a batch size. And we'll just use 64. And we'll set shuffling to true. And we'll do the same with the test, except that we don't need the shuffling because it's testing, so we have to use all the samples anyways and the order doesn't matter. Next, we create the loop that evaluates the model. So we use the test loader to get some inputs and see if the model can correctly predict the outputs. And right now the model will not be able to create the correct predictions, right? Because we haven't trained the model. We have yet to implement backpropagation. But right now, what we have is a model that can take an input and produce an output. Now we just have to create a method that can do backpropagation, so to tune the weights so that these predictions the model make will be correct. Right now, we're just creating the evaluation method that looks at the test data and sees how well does the model perform. And here to begin with, of course, it will not perform well because it doesn't know what to predict and what it's even meant to do. And what the evaluation method does is that it takes the inputs, which is of batch size 64, makes some outputs, uses the outputs and sees what is predicted, and then it checks if the labels match the predicted index. Because the labels will be from 0 to 9 and the indexes of the output neurons will be from 0 to 9. So the output neuron with an index of 5, that will also be the prediction 5. So as we can see, the accuracy is very poor, which is as to be expected. And just for fun, we can just take a look at how well it actually performs for a single batch. So these are the correct labels. And now let's see the predicted labels. And as we can see, it's pretty random. It gets some of them correct. It is clearly very biased towards predicting an 8 all the time, or a 4 or 1. But we'll create backpropagation in the next video that will tune these weights so that it gets a much higher accuracy.